Hey everyone, Miss Gaynor here. Clearly I cannot be with you today, but my voice still can. I've recorded my PowerPoint slides for today. That way you'll be able to go through these as we talk about depicting nuclear reactions. So yesterday we talked all about different types of radiation, alpha, beta, and gamma particles, and today we're going to go one step further and actually learn how to write nuclear reactions to see what happens when atoms fuse or when an atom undergoes fission and splits apart into two different things. So pretty cool stuff. Remember, we do still have our nuclear parking lot, so if you have any questions, put those on a post-it notes and stick it up on the board. I'll answer that when I get back. Now, this is the first time we've done recording PowerPoint slides, so bear with me here. We'll all be in this together. But one quick thing to keep in mind is that this is a video that can be paused. If you need more time to write something down, just raise your hand, ask the substitute to pause, and you'll be able to take time to finish taking notes. It's hard to judge how quickly we're going to move, so again, make sure if you need to stop, need more time, that you're raising your hand and asking for that. And let's get started. Here we go. So quickly to review the answers from our do first. I'm going to be putting up the answers here now. So make sure that if you got these answers incorrect, that you're copying them down now. A couple key things to remember. Whenever we have something written like this, the number after the element is the mass number. So if we have carbon 14, that means that carbon, where'd my little mouse thing go? There it is. If we have carbon 14, that means that carbon has a mass of 14. Potassium 41 has a mass of 41. And lead 206 has a mass of 206. We know that the mass number is equal to protons plus neutrons, and the atomic number is the number of protons. So take another 30 seconds to make sure that you have these answers down, and then we're moving on to atomic symbols. So once again, make sure that you have this diagram down. When we have things in the XAZ format, X is the chemical symbol. So Pb for lead, Na for sodium, that's X right here. Next up we have A. A is the mass number. So the number on top is the mass number. That's the number of protons plus the number of neutrons. And Z, as I look for my little mouse symbol here, Z is the atomic number. This is the number of protons. So Z, we've got number of protons, and A on top is the mass number. That's protons plus neutrons. Now when we showed nuclear reactions, there's two key points to keep in mind. The mass numbers are going to be the same on both sides of the equation. And the atomic numbers are also going to be the same on both sides of the equation. Let's take a look to see how this works out. The mass numbers are going to be on the same on this side of the equation as on the right side. So on the left side, we've got mass numbers of 9 and 4. 9 and 4 add up to 13. Let's check on the right side. Here we've got 12, and here we've got 1. 12 and 1 are also going to add up to be 13, so this checks out. We've got the same mass numbers on the left and the right sides of the equation. It's the same for atomic numbers. It needs to be the same on the left side as on the right side of the equation. On the left side, we've got atomic numbers of 4 and 2. 4 and 2 add up to 6. Now let's take a look on the right. Here we've got atomic numbers of 6 and 0. 6 and 0 also add up to 6. So this checks out. The atomic numbers are the same on the left side and on the right side of the equation. So when we want to find the missing nucleus, we want to find the missing chemical symbol here, we're going to follow our two rules. We know that the atomic numbers are the same on both sides, and the mass numbers are the same on both sides as well. So let's take a look at how this works out. For the mass numbers, we know that 234 is going to be equal to 4 plus whatever this mass number is. So we subtract 4 from this side, 4 from this side. We end up with this mass number is going to be 230. 230 plus 4 equals 234. It's the same for the atomic numbers. The atomic numbers on the left are the same as the atomic numbers on the right. So we can set this up as 90 is equal to 2 plus this atomic number. Subtract 2 from each side, and we end up with the atomic number is 88. So our last step is to write the chemical symbol. We know the atomic number is 88 and the mass number is 230. Looking at our periodic table, if it has an atomic number of 88, if it has 88 protons, that means this element is going to be radon. So we can write this as radon having an atomic number of 88 and a mass number of 230. Let's try another problem. Here, we have carbon-14 is undergoing beta decay, because we know it's decaying into a beta particle and a mystery nucleus. So let's solve for this symbol here. Once again, we know the mass numbers are going to be the same on both sides. 14 is equal to 0 plus whatever A is, whatever the mass number is on the right. Subtract 0 from both sides. A is going to be 14. So we know the mass number is going to be 14. Now let's find the atomic number. Again, the atomic numbers are the same on both sides. So we can write this as 6 is equal to -1 plus Z plus the atomic number on the right. Now this step's a little tricky because it involves negative numbers. So remember, if we have 6 is equal to -1 plus Z, in order to get Z by itself, we want to add 1 to each side of the equation. So we add 1 to the left, add 1 to the right, and we end up with Z equals 7. So this means our atomic number for this element is going to be 7. So last but not least, we want to write out our element symbol. And we can write this as the atomic number is 7, the mass number is 14. If it has 7 protons, this element must be nitrogen. So, these are all called transmutation reactions. That's a fun word to use. Transmutation means that the elements themselves change. So now, whenever we see a transmutation reaction, it's when we have one element decaying into an entirely different element. So this is really cool science right here. This is alchemy. It can only be used in particle accelerators, but really cool science that we've got going here. So our last step is to be able to write out our nuclear decay equations ourselves. Now I've written the steps for the first problem, so you can follow along with me for the first problem, and then write out the steps on your own for the problems number 2 and number 3. So the first step, we always want to start off with step number 1, is to write out the chemical symbol for our starting elements. So we want to write out our symbol for uranium-238. So we can start by writing a U for uranium. We know it's going to have a mass of 238, so we can write 238 as our mass number. And if it's uranium, it's always going to have 92 protons. So it's going to have an atomic number of 92, because all uraniums have 92 protons. Then we want to follow it with an arrow. So after the symbol, we're going to write an arrow to show that it's decaying into something else. Our next step is to write the symbol for the type of decay. Now the problem tells us this is alpha decay. So that means we're going to write an alpha particle. So let's look back at our notes, see what the symbol for an alpha particle is. And by looking at our notes, we can see that an alpha particle is going to have an atomic number of 2, mass number of 4. It's a helium. It's a helium atom. So now we've got our starting elements. We've got the type of decay. Our next step is to find the missing element here. Once again, we know that the mass numbers are the same on the left and the right, and the atomic numbers are the same on the left and on the right. So we know the mass number, 238, is equal to 4 plus whatever this mass number is. Subtract 4 from each side, and we have a mass number of 234. Now let's find the atomic number. The atomic number is going to be on the same on the left and on the right. So we can set this up there's our mass number on top. We can set this up as 92 is equal to 2 plus whatever this atomic number is. Subtract 2 from each side. We know that our atomic number is going to be 90. So we can write 90 here. We've got an atomic number of 90, mass number of 234. If it is an atomic number of 90, that means this element is going to be thorium, just like the superhero. So we've got thorium 234. Keep in mind, this was when we used an alpha particle. So in our next problem, we're going to see what happens when we have beta decay. We're going to follow the same steps we did in the last problem. The first step is to write out the chemical symbol for iodine 131. So we will start by writing I for iodine. It has a mass of 131, and all iodines have an atomic number of 53. So now we've got our chemical symbol for iodine 131. Next step, we write an arrow after. Next step is we write the symbol for beta decay, because this problem involves beta decay. So we're going to write the symbol for beta decay here. It's a little E symbol. It has an atomic number of -1 and a mass of 0. Our next step is to figure out our missing element here. So the mass numbers are going to add up. 131 is equal to 0 plus this mass number. Subtract 0 from both sides, and our mass number is going to be 131. Same thing for the atomic number. We can write this as 53 is equal to -1 plus this atomic number. So, add 1 to each side, and we end up with our atomic number is 54. So now we know our atomic number, our mass number. Last thing is to write our chemical symbol. If the atomic number is 54, that means the element is going to be xenon. So what we have here is our nuclear decay equation for when iodine 131 undergoes beta decay. Last but not least, we're going to look at a gamma ray equation, the favorite ray of the Incredible Hulk. So, we're going to start with step 1. We're going to write out our chemical symbol for carbon-14. Carbon-14, symbol is C. It has a mass of 14 and an atomic number of 6. So we've got our symbol for carbon-14. Next step is we're going to write the symbol for gamma decay, for a gamma ray. Now gamma ray, what we have here, this is the Greek symbol for gamma. It has a mass of 0 and an atomic number of 0. Last but not least, we want to solve for our missing problem, for our missing elements. The mass number, 14, is equal to 0 plus this mass number. Subtract 0 from each side. Our mass number is 14. Same thing goes for the atomic number. There's 14 up there. The atomic number is going to be the same on the left and the right. So we can write this as 6 is equal to 0 plus this atomic number. Subtract 0 from each side, and our atomic number is going to be 6. So now we've got the mass number up here, atomic number down here. 14 on the left, 14 on the right, 6 on the left, 6 on the right. If it has 6 protons, we're going to look at our periodic table. This element is going to be carbon. So this is kind of an interesting equation. Whenever gamma rays are involved, the element doesn't change because gamma rays have no charge and no mass. They don't change the number of protons, so you end up with the same element that you started with at the beginning. So what you're going to do now is you're going to be working through the rest of the practice problems in your packet. Anything that you do not finish is homework, and if you would like to check your answers, then the substitute has the answer key. Good luck, have fun, and I will see you guys on Monday. Remember that we do have a quiz tomorrow on chemical, physical, and nuclear changes. So make sure you're looking through your notes from Monday, Wednesday, and today, and getting prepared for our quiz tomorrow. Anything you do not finish is homework for tonight, And I really enjoy the article in the back of your packet, so if you have time, definitely give it a read. If you like science and superheroes, you'll love it.